until official time.
Mm-hmm.
So yeah, very great pleasure to have Frances Kirwan from Oxford University speaking today, and she will be talking about moment maps for non-reductive group actions in Kähler geometry.
Thank you very much. So many thanks to all the organizers for the invitation. So let me see whether I can change slides. Okay. Yeah, no, I can't. Well, I can do it that way. So can you see my mouse moving around?
Yes, 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 yes.
Right. Okay, fine. So yeah, so what do I want to talk about? Well, basically, it's been known for decades that there's a close relationship between classical geometric invariant theory, GIT, and constructing quotients for complex reductive group actions on algebraic varieties, and indeed in Kähler manifolds with the notion of symplectic reduction and taking quotients in symplectic geometry and moment maps, and you can use these moment map descriptions of GIT quotients to understand cohomology, at least the rational cohomology of these quotients in various ways. So so what I want to talk about is a way of generalizing that picture of moment map descriptions of quotients by reductive group actions to suitable non-reductive group actions and non-reductive GIT that's been developed over the last decade or so. So I will start off with a very brief reminder of classical GIT and symplectic, the links with symplectic reduction, and then a little bit about the non-reductive version of GIT that I want to talk about, and then say something about symplectic implosion, which is a symplectic description due to Lisa and others, Gilman, Jeffrey Shamar, of certain non-reductive GIT quotients being described in a from a moment map point of view. And then I want to, but that's not exactly the non-reductive setup that I'm interested in. Oh, I should have said it was on my title page that this is joint work with Gergely Berczi, and there's a paper on the archive which we revised in September, though it was written a couple of years ago. So what Greg and I want to do is think about the idea of a moment map from a slightly different point of view. We call them omega moment maps, so that well, first of all, you can think about that for complex reductive group actions, but then it sort of naturally leads you, or more naturally leads you, to the non-reductive GIT setup, and hence to a moment map description of these non-reductive GIT quotients. And as I said, the main motivation for having such a moment map description is that we can then try and, at least in nice cases where we get quotients that are non-singular or at worst orbifolds, we can get applications to understanding the cohomology of these quotients, and in particular getting formulas for intersection pairings, sort of integration formulas. And if I have time, but I may well not, I'd like to just briefly mention the application in the area of hyperbolicity to getting polynomial bounds in the situations of the Green-Griffiths slang and Kobayashi conjectures about hyperbolicity. So yeah, so that's
geometry.
plan. So sorry, was there a question? Do interrupt and ask questions if people have questions. Okay, so so just as a quick reminder, classical GIT developed by David Mumford in the 1960s. I'll work over the complex numbers. If we have a complex reductive group and it's acting on a complex projective variety and acting linearly in the sense that we've got a lift to an ample line bundle, or essentially equivalently, we've got X embedded in a projective space and the action given by a representation of our reductive group G, then we can go from X, or really X on the line bundle, to its homogeneous coordinate ring, which is a finitely generated graded complex algebra. And then the fact that we've got a linearization means that we have a group, an action of the group G on this homogeneous coordinate ring, and we can look at the subring or subalgebra of invariance. And because G is reductive, that will itself be finitely generated and therefore correspond to a projective variety, the associated projective variety, which we think of as the GIT quotient of X by this group action. And from a geometric point of view, the inclusion of the invariance in the homogeneous coordinate ring of X gives us a rational map in the other direction. And this rational map, we can restrict it to the so-called semi-stable locus, which is an open subset where the rational map becomes a morphism, well defined. And that morphism is obviously then going to give you something G invariant. But what's not obvious but is true is that it's actually surjective. And then, but it's still not necessarily just giving us a topological quotient of the semi-stable locus, but we can restrict further to the stable locus, and then we do get a geometric quotient of the stable locus with a projective completion, a compactification, which is our GIT quotient. And topologically, the GIT quotient is the semi-stable locus quotiented by the equivalence relation, which is often called S equivalence for Széchenyi, which where we have that two semi-stable points are equivalent if and only if the closures of their orbits, their G orbits, meet in the semi-stable locus. And every equivalence class contains a unique polystable orbit, so a semi-stable orbit which is closed in the semi-stable locus. So each equivalence class is represented by a unique polystable orbit. Okay, so then one of the very nice things about classical GIT is that we have these nice Hilbert-Mumford criteria for stability and semi-stability. So we don't need to know what all the invariants are to know what the semi-stable locus and the stable locus, what they are. And the exact criteria are not going to be crucial, but in terms of convex polytopes. So then, as I'm sure this audience knows, we have the concept of symplectic reduction, symplectic quotients, which link up with classical GIT. So if we have a complex symplectic manifold and a compact Lie group with a moment map, so a Hamiltonian action, then well, we can talk about the moment map, and in particular we can look at the case where we've got a Kähler action and holomorphic action which is also Hamiltonian, and then extending to the complexification of the compact group, which will be a reductive group. And then we can look at Marsden-Weinstein reductions at well, a regular value, then we'll get a symplectic orbifold. And in particular, when we take the reduction at 0, we have the so-called symplectic quotient, which is the inverse image of 0 under the moment map quotiented by the compact group. And in the Kähler case, if we've got a regular value, if 0 is a regular value of the moment map, then the symplectic quotient can be identified with a quotient of an open subset of X, the Kähler manifold, by the complexified group action, and it inherits a Kähler structure from putting together the two sides of this identification. And to some extent, you can think of that as a consequence of the fact that if you take the gradient of the moment map in the direction of some element of the Lie algebra, then that's just I times the infinitesimal action of the element of the Lie algebra. And then if 0 is not a regular value of the moment map, then you get a stratified symplectic or Kähler structure, but with more serious singularities that lots of people have looked at and studied. And if you're in the situation of the algebraic geometry situation with a linear action of the complex reductive group G, and so that will be the complexification of the maximal compact subgroup K. If you've got a linear action on complex projective variety, say sitting in a projective space via a linear representation, then we can choose coordinates so that the compact group is acting unitarily, and then we can use the Fubini-Studi Kähler form as our Kähler structure, and we can write down explicitly a moment map for the action of the maximal compact group K. And then it turns out that you can describe semi-stability and stability purely in terms of the moment map and the complex group actions. So a point is semi-stable if and only if the closure of its orbit, its G orbit, meets the 0 locus of the moment map, and it's stable if and only if its actual orbit meets the regular part of the 0 locus, so where the derivative of the moment map is surjective. So then that tells you straight away that you've got an inclusion of the 0 locus of the moment map in the semi-stable locus, and you can compose that inclusion with the quotient morphism to the GIT quotient. And so then you get an induced map from the symplectic quotient to the GIT quotient, the symplectic quotient by the compact group K to the GIT quotient by the complexified group G. And it turns out that that's a homeomorphism, and the two sides have slightly different structures, but they're compatible via this map, this identification. And it's this essentially this sort of picture describing semi-stable locus and stable locus in terms of the moment map that allows you to construct Kähler quotients as well. So we have this nice picture in the classical setup of GIT quotient and identification with a symplectic quotient, so description in terms of a moment map. So then we can ask, well, what about GIT if we've got a group which is not reductive? So then there's an obvious immediate problem, which is that the invariants of the homogeneous coordinate ring in this case are the algebra of invariance is not necessarily finitely generated, so we don't get an associated projective variety. So the question is, can we define some reasonably nice sort of quotient variety when the group is not reductive, and can we understand it geometrically? And so people over the last few decades have given different definitions, so the range of definitions of sort of stable locus and semi-stable locus, and with a geometric quotient, a nice quotient of the stable locus, and different sorts of versions of quotient in some sense of the semi-stable locus. So so you can have something which Brent Doran and I called an enveloping quotient. So the semi-stable locus going to some sort of GIT quotient of x by g, but that quotient is not necessarily projective, and the morphism to it is not necessarily surjective, and you can't even get around one of those problems by modifying. I mean, you can't even say, well, if we're not getting something projective anyway, why don't we just get a morphism which is onto by looking at the image of the morphism from the semi-stable locus. But that doesn't work because the image in general is just a constructible subvariety. It's not actually a subvariety itself. And the Hilbert-Mumford criteria in these situations don't obviously generalize. So you can do something in general, but it's a bit of a mess, really. So what I want to talk about is a situation where you've got a much nicer version of GIT for non-reductive groups. And the basic idea is that the unipotent, so a linear algebraic group over the complex numbers is a semi-direct product of its unipotent radical, which is maximal normal unipotent subgroup, and a reductive group. So the problematic part is the for non-reductive groups is the unipotent radical. So we have a good situation if our unipotent group is graded in the sense that it's got a one parameter group of automorphisms, so a homomorphism from C star to the automorphism group, such that all the weights of this C star action, the induced action on the Lie algebra, are strictly positive. And so we call such a group a graded unipotent. And then we can look at the semi-direct product U hat of this group U and the C star with respect to this this group of one parameter group of automorphisms. So if we have a group like this.
Can I ask, in terms of concrete examples, what should one have in mind? Strictly upper triangular matrices, for example?
Yes. So for unipotent groups, essentially, they're subgroups of the strictly upper triangular matrices in GLN for some n. Yeah. Mm-hmm. Yeah. And so then you can think of the C star as acting as being a diagonal one parameter subgroup of that relevant GL, but you need it to normalize the subgroup U of the upper triangular matrices. So certainly, if you took all the upper triangular matrices, then that would be fine. That would be graded unipotent. Mm-hmm. But not every unipotent group can be graded. Well, yeah, so that's another story, I guess. So I want to think about the situation where we've got a one of these groups U hat. So we've got unipotent group semi-direct product with the C star, and it's acting on a projective variety and acting linearly. And so it turns out that that as long as you're prepared to change the linearization by a suitable character or rational character, which from a moment map point of view for the C star action is just the same as adding a constant, a suitable constant to the moment map, then provided you're prepared to do that, then GIT for the U hat action is, at least in some ways, in many ways, almost as well behaved as for reductive groups. And so in particular, that works whenever you've got a linear algebraic group H with what we call internally graded unipotent radical, in the sense that we've got H as a semi-direct product of its unipotent radical and a reductive group, Levy subgroup R. And if the Levy subgroup R has a central one parameter subgroup which grades the unipotent radical of the group H, then what we can do is, if we know that we can quotient by find a reasonably nice GIT quotient by U hat, then we can first quotient by U hat, and then we'll have a residual action of the of H mod U hat, which is just the quotient of R by its central one parameter subgroup. So that will be a reductive group. So so the idea is that lots of there are a lot of these internally graded unipotent, well, linear algebraic groups with internally graded unipotent radicals. In particular, any parabolic subgroup of a reductive group will have this property. So here's the technical result, which is about the well, the nicest sort of action of one of these U hats, so semi-direct product of a unipotent group with a C star multiplicative group which is grading it. So the conditions that we want are that we've got this this linear action, and we want to assume this condition star, which is sort of a semi-stability coinciding with stability sort of criterion, which is the nicest sort of case in the reductive setup, and also the nicest case here. So the condition star says that if you look at the connected components of the one parameter subgroup, where the one parameter subgroup acts on the fibers of the dual of the line bundle, so the tautological line bundle on Pn with minimum weight. So the grading condition tells you that those are essentially the fixed points where you've got most chance of trivial U stabilizer. So the U action is moving those points with fixed points with minimum weight in the direction towards higher weights, and you've got the most chance of that movement being always non-trivial, as it were. So so the condition you want is that everything in this Z-min should have trivial stabilizer in under the U action, and that is a sort of a condition that you can expect to happen, at least in sort of nice cases, and you can expect to be able to maybe, if necessary, do some blow-ups to get this condition satisfied, at least if the generic stabilizer in X is trivial. So So that's the semi-stability coinciding with stability condition. And then we also, as I said before, need to be prepared to twist the action, the linear action, by a rational character in such a way that 0 lies just above the minimum weight for the C star action. So twisting by a character is just meaning that you're multiplying the lift of the action to the line bundle by this character, or you're maybe taking a 10th power of the line bundle and then multiplying it by a character, and that's essentially multiplying the original action by a rational character. And we want to do that so that 0 lies just above the minimum weight. So I'll say a little bit more about that in a minute. And then if we've got these two conditions, then it turns out that the algebra of invariance is finitely generated. So we do get a genuine projective variety associated to the algebra of invariance. And moreover, that projective variety is indeed a geometric quotient of the semi-stable locus for the U-hat action, which is the same as the stable locus of the U-hat action. And this locus has a very simple Hilbert-Mumford description. So we've got a very nice picture here. So to describe the Hilbert-Mumford condition, let's first of all think about the C star action, the multiplicative group action. So that's acting linearly on X, and we can look at all the weights of that linear action. And as I said before, we have Z min, which is the fixed points where the that weight is minimal. And then we can also, and that will be a closed subvariety of X. And then we'll also have an open subset of X, this X naught min, which is essentially the Bialinitsky-Berula stratum corresponding to Z min. So it's all the points in X such that if you take the limit of the C star orbit, you take lambda t acting on X, and you take the limit as t goes to 0, then you'll get an open subset's worth of points where that limit is actually in Z min, has minimal weight. And if you twist by a character or rational character so that 0 is strictly between the minimal weight and the next weight up, then it turns out that the stable locus for the C star action, which is the same as the semi-stable locus for the C star action, is just the complement of Z min in X naught min. So that just comes from Hilbert-Mumford, the easiest case of Hilbert-Mumford for just for a multiplicative group action. And you can always achieve that condition that 0 is strictly between the minimum weight and the next one up by multiplying the linearization by a suitable rational character. And so slightly more generally, we say that a linearization is well adapted to the action of U hat on X, or more generally, if we've got an H, which is a semi-direct product of unipotent radical and reductive group R with a central one parameter subgroup, which is grading U, then in that situation, we can always make a linearization, what we call well adapted, by multiplying it by a rational character, so that 0 got shifted so that it's now just above that minimum weight. So it's lying between the minimum weight and the next one up. But if we've got our bigger group H that we're worrying about, then it might not be enough to just have it between the minimum weight and the next one up. But we need to have it sort of sufficiently close to 0. And the general sort of variation of GIT sort of picture tells us that if we have it sufficiently close to 0, but strictly bigger than 0, then exactly where it is shouldn't matter. So anyway, if our condition star holds, so that semi-stability coincides with stability in this sense, then we get the semi-stable locus and the stable locus are both x naught min, and then the set theoretic, the complement of the U sweep of Z min in x naught min. So x naught min itself will be U invariant, but Z min will not in general. And so if you like, it's the intersection of the U sweeps of the x naught min take away Z min, the stable locus for the C star. So the stable locus for U hat is the intersection of the stable loci for all the GMs, all the multiplicative groups in U hat, and they're all conjugate to each other by U. So that's the Hilbert-Mumford picture in this very nice situation. And so yes, so if we have this this picture as before, with H a semi-direct product of unipotent radical and reductive group with a central one parameter subgroup grading the unipotent radical, then we will say that we have stability coinciding with semi-stability for H if the condition that we had before for U hat holds, and also when we look at the induced action of R, or rather R modulo the one parameter subgroup, then for that reductive group action on Z min, we have semi-stability coinciding with stability, and we have stable points. So that's the nicest situation, and a corollary really of well, it's not quite a corollary, but a generalization of the result that I had before is that if you've got a well-adapted linear action of this group H, which satisfies semi-stability coinciding with stability for H in this sense, then the algebra of invariance is finitely generated, and the associated projective variety is just a geometric quotient of the inverse image of the stable locus for this reductive action on Z min under this limiting map P, and then you have to take away the U sweep of Z min. So that's the sort of picture that would like to have a moment map description for it. So yes, so as I said before, examples of such groups H would be parabolic in a reductive group, or the automorphism group of a complete toric variety has this form too of internally graded unipotent radical. So as I said, in the reductive case, the quotient can be identified with a symplectic quotient, and this has applications, at least in the good case, for reductive quotients when semi-stability coincides with stability, which we can achieve by doing suitable blow-ups of X, provided that we've at least got some stable points. So the applications in this situation, we can understand, try and understand the rational cohomology, so the Betti numbers, the rational cohomology ring, the intersection pairings on the quotient. So that all works in the reductive case. So it would be nice to have a similar description of the quotient in terms of some sort of moment maps, more generally, at least when in this nice setup when semi-stability coincides with stability. And then more generally, we can try and get that by blow-ups. So let's look at the simplest example where we've got one-dimensional unipotent group, so just the additive group C+, and U hat is semi-direct product of C+ and C star, the multiplicative group, where this is a genuine semi-direct product, so not just a product. So then we have, if this is acting linearly on a projective space, then we can always choose coordinates such that the C star acts diagonally and the generator of the additive group is in Jordan normal form. And that tells us that the additive group action extends to an action of SL2, where we think of the additive group as the maximal unipotent in SL2, the strictly upper triangular matrices in SL2. And at least if you replace U hat by a cover, then the action of U hat extends to SL2 cross C star, where U hat is sort of diagonally embedded in SL2 cross C star. And in this situation, you do always get finitely generated U invariants. And so you can talk about the GIT quotient, proj of the invariants. And the reason, well, one way to show that you've got finitely generated invariants is that you can describe, so G is SL2 here, invariants, C+ invariants on Pn are essentially G invariants on this twisted product, G cross Pn quotiented by the additive group. And because the additive group action on projective space extends to SL2, we can untwist that product, and we just get G mod C+ cross Pn. And G mod C+ is just C2 minus the origin. So then that sits inside C2, obviously, with complement of codimension 2. So the invariants, we can think of the invariants as G invariants on C2 minus the origin cross Pn, but they don't see the fact that the origin is missing because it's only codimension 2. So they all extend uniquely to G invariants on C2 cross Pn. And that's, well, and if we choose the linearization appropriately, we can think of those as all extending to invariants on P2 cross Pn, which vanish on the line at infinity. And so we end up seeing that the non-reductive GIT quotient can be identified with the reductive GIT quotient of P2 cross Pn by SL2. And so we know how to understand that geometrically, and we can work out semi-stable and stable loci and quotients and so on. So in particular, you can find an example of when you get some not surjection from the semi-stable locus to the quotient, and you get really understand geometrically what's going on in this situation. But you can also notice that if you quotient not just by the C+, but by the U hat, which is the C+ semi-direct product C star, then provided you you modify this linearization by an appropriate rational character, then you can make sure that all the so-called boundary points in the quotient by the additive group, which came from the missing origin in C2, you can make them all become unstable for the induced action on of C star, without making everything unstable, which wouldn't be good. And so that you, in that case, get a nice surjective morphism from the semi-stable locus to the non-reductive GIT quotient. So that's the sort of example, that's the basic motivation for the more general set up that that you can actually prove essentially by induction on the dimension of the unipotent group and reducing to this situation. So symplectic implosion, as I said, gives you a way to give a moment map description for some non-reductive GIT quotients, which don't cover all the ones that we're interested in, but do cover this case when you've got an additive group action extending to an SL2 action. So so the ingredients here are a symplectic manifold, Hamiltonian action of a compact connected, let's say connected group K, and we fix a maximal torus. We fix a positive Weyl chamber in the dual of the Lie algebra of the maximal torus. And we look at the stabilizer K zeta of anything in that positive Weyl chamber under the coadjoint action. And then Gilman, Jeffrey, Shamar define the implosion or the imploded cross section of X to be the inverse image under the moment map of the positive Weyl chamber, but then with some collapsing on the boundary. And the collapsing is defined by saying that if you've got 2 points with the same image under the moment map, then you identify them if they're in the same orbit of the commutator subgroup of the stabilizer of that point under the coadjoint action. And it turns out, yes, and so in the SU2 case, you're just, for slightly perverse reasons, I'm taking the positive Weyl chamber to be the negative real axis. And so then you're taking the inverse image under the moment map of the interior, the open interval minus infinity 0, and then the inverse image of 0, and you collapse that by the SU2 action. So this implosion inherits a stratified symplectic structure and a torus action with a moment map just given by the restriction of the original moment map. And we can describe the general implosion in terms of a universal implosion or universal imploded cross section, which is the implosion of the cotangent bundle of the compact group. And it turns out that universal implosion is an affine algebraic variety. So that tells you that if X is algebraic, then we end up with the implosion being also algebraic. And so spelling that out a little bit more, so if we've got our complex reductive group G, which is the complexification of K, we look at a maximal unipotent subgroup of G normalized by the maximal torus T. Then the quotient of this G mod, the maximal unipotent, is a quasi-affine variety whose algebra of regular functions is finitely generated. It's just the invariance for the unipotent action on the regular functions on the complexified group, which is affine. And so that means that we get a canonical affine completion. So an affine variety, usually very singular, though not in the case when K is SU2, when we just get C2 as we've seen before. So we've got this canonical affine completion, and Gilman, Jeffrey, Shamar show that it has a K invariant stratified Kähler structure, which symplectically is just giving us the universal implosion. And so that means that if we've got an affine or projective, or indeed projective over affine variety, the situation that works nicely for GIT, and if it's acted on linearly by the reductive group, and we restrict the action to the maximal unipotent subgroup, then the quotient of X by that maximal unipotent subgroup, the GIT, non-reductive GIT quotient, can just be described in terms of the implosion. And we can generalize this, and we can replace the maximal unipotent with the unipotent radical of any parabolic. But again, we're needing that X should be acted on linearly by the whole reductive group, and then we just look at the restriction of the action to the unipotent radical of a parabolic. And then in a fairly recent paper, Greb and Miebach study a much more general situation here of just essentially an arbitrary unipotent subgroup U of a reductive group G, and where they don't require G to act on the space that you want to take a quotient of by U, but you have U acting on Y, and U's a subgroup of the reductive group G, and Y's a submanifold of X acted on by G. So you can say things in that more general situation, and that's essential. Well, that's very close to what I want to talk about, except that in this situation, typically you end up with things that are very nasty and singular, and so we want to end up with things that are non-singular or close to being non-singular. So we don't want to just look at the unipotent group. We want to have more a bigger group acting with a grading one parameter subgroup, and we want to be able to get things that have at least some chance of ending up as being sort of at worst orbifolds. So if we go back to this simple example, then if we take the projective space and we quotient by the additive group, then from the point of, and this is the situation of symplectic implosion with the additive group maximal unipotent in SL2. So we can describe it in terms of the moment map for the SU2 action, the inverse image of the positive Weyl chamber, modulo this collapsing on the boundary. And so then the problem is that this collapsing on the boundary can be a bit messy, and particularly if X is sitting inside the projective space and is not invariant under the SL2 action or the SU2 action, then that can get quite messy. But if we quotient further by the multiplicative group action, then that means that we have to intersect with the pre-image under the circle moment map of whatever psi we're choosing to shift the moment map by, and then we have to quotient by the S1 action, and then we have to potentially do some collapsing. But if we choose our psi in such a way that that we don't meet the boundary, and indeed that so that we have that the inverse image under the SU2 moment map of the Lie algebra of the maximal torus intersect the inverse image of psi under the circle moment map, if that intersection is completely contained in the pre-image under the SU2 moment map of the interior of the positive Weyl chamber, then we're in really good shape, because then we don't have to worry about the collapsing on the boundary at all, and we can just describe our non-reductive GIT quotient as the pre-image of 0 under the projection of the SU2 moment map onto the orthogonal complement of the Lie algebra of the maximal torus, which in some sense can be thought of as a U moment map for the U action, the unipotent group. And then we have to also impose the circle moment map condition and quotient by the circle. So then we get essentially a description as the inverse image of 0 under a moment map, in some sense a moment map for the U hat action, and then quotiented by the maximal compact subgroup S1, the circle of U hat. So that's the sort of picture that we want to have more generally. And so it turns out that one way to sort of set that up and interpret moment map for the U-hat action is to work for these slightly different notion of a moment map. So we called an omega moment map. So the basic point here is, if we go back to a compact Kähler manifold and a holomorphic action of a complex reductive Lie group G, if we choose a maximal compact subgroup of G, then the dual of the Lie algebra, the real dual of the Lie algebra of this compact group K, embeds in the complex dual of the Lie algebra, the complex Lie algebra of the complex group G, as just the elements of the complex Lie algebra which take real values on the Lie algebra of the compact group. And so from that point of view, instead of fixing the compact group and assuming that the Kähler structure is invariant under this compact group and having a moment map from which takes values in the real dual of the Lie algebra of the compact group, we can think of composing that with the inclusion into the complex dual of the Lie algebra of the complex group, which is really what we're interested in. And then we have the issue about, well, how do we choose the Kähler structure? Because we'd want it to be K invariant, but it makes perfectly good sense to choose a whole G orbits worth of pairs K and omega, where K is a maximal compact subgroup and omega is a K invariant Kähler form on our Kähler manifold. And then we can try and interpret the original notion of a moment map for the K action in terms of what we call an omega moment map, which goes from the product omega, this orbit, this G orbit omega cross Y, to the complex dual of the Lie algebra of the complex group. So we'll call such a G orbit omega a G equivariant Kähler structure. And then we can just ask for a smooth G equivariant map from this product omega cross Y to the dual of the Lie algebra of the complex group. And we can just ask that if we restrict it to taking any pair K omega in capital omega, then we're just getting the composition of a moment map in the usual sense for the K action with respect to little omega, composed with this embedding of the dual of the Lie algebra of K in G star. So I am getting short of time, but just to say that so then you can interpret the moment map equation. You get a slightly modified differential equation for the omega moment map, where you describe it in terms of the Hermitian metric corresponding to the Kähler form. And then this is something that it makes sense to restrict to the non-reductive, or to extend in a sense to the non-reductive GIT or the non-reductive case where we've got a non-reductive action. So if we've got a non-reductive group H acting on a compact Kähler manifold X, then to find what we call an H equivariant Kähler structure on X, we want both a reductive group G which contains H and potentially a bigger Kähler manifold Y which contains X, such that the reductive group G acts on the Kähler manifold Y and its action restricts to an action of the non-reductive group on the original Kähler manifold X. And then we want to pick a G-equivariant Kähler structure on Y with respect to this G. And then in that G-equivariant Kähler structure, which will be an orbit of pairs, a G orbit of pairs K omega, we want to choose an H orbit in that G orbit consisting of pairs K omega, where K is a maximal compact subgroup of the big group G, but its intersection with H is maximal compact in H. So that's a bit of a mouthful, but it seems to be a good structure for taking Kähler quotients by these non-reductive groups with internally graded unipotent radical. So in this situation, then it's fairly easy to just take the definition, the differential equation for the omega moment maps in the reductive case, and just restrict to the non-reductive case. And so we get the differential equation, which can be expressed in terms where, so you need to think about where the bigger Kähler manifold Y comes in, and it comes in this part of the equation where you're looking at the K invariant involution on the big reductive group G, because although A is in H, or the Lie algebra of H, when we apply this involution to it, it's not necessarily in H, and so the infinitesimal action, the tangent vector that we get here, is not necessarily tangent to X, but only to Y. So that's where sort of Y comes into this picture. And so it turns out that using these this notion of a moment map, then provided that we're in the really nice situation of a well-adapted action on a smooth complex projective variety, and we choose an H equivariant Fubini-Studi Kähler metric, and then we can write down the corresponding moment map just as we can in the reductive case. If we have H stability coinciding with H semi-stability, then it turns out that if we think about things in this moment map picture, we get that 0 is a regular value of the moment maps that we find, and we can describe semi-stability and stability in terms of these moment maps. And the quotient, we get this surjective local diffeomorphism of orbifolds from the pre-image of 0 under these sort of moment map like thing, quotiented by the maximal compact subgroup K intersect H to the non-reductive GIT quotient. So I'm really running out of time, but using this picture, we can describe Betti numbers. You don't really need the moment map to describe the Betti numbers of the quotient in this situation. But where you do need the moment map is to understand the cohomology ring and intersection pairings. So this is following the ideas of Sean Martin in the reductive case. You have a picture, a moment map picture that you can relate to the moment map picture for quotient by a maximal torus in this non-reductive group H. And you can then use that to describe, to give a description of the cohomology ring, essentially in terms of the cohomology of the quotient by the maximal torus. And what you really use to prove that is an integration formula which relates integration over the non-reductive GIT quotient to integration of a related cohomology class by the on the quotient by the maximal torus, which is we understand very well. So I think that's the last slide before the hyperbolicity slides, and the time is now the end of my hour. So I think I should stop there, and thank you for your attention, and apologies for not having time to get to the hyperbolicity applications. So thanks very much.
Well, thanks a lot for the talk. So do we have questions? Yeah, Lisa. Lisa, you're muted.
I have one question. Page 15, you had an application which involved SL2. Does that generalize to other groups such as SLN?
So let me go back to page 15, sorry. Yes and no. So it generalizes to the case when you have a maximal unipotent in a reductive group, which is essentially the symplectic implosion situation. So in that situation, you always have finitely generated invariants, and you can prove that by sort of generalizing this picture where you replace C2 by the canonical affine completion of or the universal implosion for the reductive group modulo its maximal unipotent, and then you can essentially go through this argument. But what you need then is that that the action that you're interested in has to extend, the unipotent action has to extend to the full reductive group, and that's great if you have that situation, but if you want to understand situations of non-reductive group actions where you don't have something of that form, where you've got an extension of the action to a nice bigger reductive group, which is going to which you've got a Gross-Hand subgroup of essentially, then you need to use other methods. So here in this the really nice thing about the additive group is that at least if you look at the ambient projective space, then the action will automatically extend to from this maximal unipotent, which is C plus, to the SL2, and so you're now in the situation where you can use symplectic implosion, whereas in general you can't. And then what you want to do is, if you've got a general unipotent, more general unipotent group, you can always find a sequence of subgroups such that the subquotients are all just C plus, so you can try and they're normal subgroups. You can try and quotient by one C plus at a time, and then that works nicely, except that you have to be very careful to so at each stage you just can't assume that you're working with a projective space at each stage, because even if you started off with a projective space, by the time you've quotiented by your first U plus, then you've got something that isn't a projective space. And so you do have to be careful about how you extend these C plus actions to SL2 on ambient projective spaces, and that's really why you need this this extra C star to help regulate things when you do this inductive process.
Thank you very much.
Yeah, other questions? Anton.
Hello, thank you
Hi.
for a nice talk. In terms of examples, I was wondering, are there examples given by moduli of flat connections? Suppose you got moduli of flat connections for something which is not reductive, but of course you may still have a quadratic Lie algebra, right? In solvable or nilpotent case, would some of those examples fit into your machinery or not at all?
So I haven't thought about exactly that sort of situation. I mean, what certainly has been one of the motivations for all of this was looking at unstable moduli of sort of unstable objects, and so in particular for thinking about bundles or sheaves or connections, and thinking about the if you fix the hard and narrow Riemann type and trying to get moduli spaces of those, and they that essentially comes down to looking at quotients by parabolics in reductive groups, and that very much does fit into this sort of picture. So yeah, the two main motivations were partly this trying to understand quotients of unstable strata and unstable moduli of unstable objects, and then also this this hyperbolicity setup where you're looking at the reparameterization groups of for jets, for jet bundles, and that's those reparameterization groups are non-reductive groups that have this structure of internally graded unipotent radicals.
In fact, do you want to briefly show us those last slides that we missed?
Sure. Yep. So I think there are 2 or 3 of them. So the idea of hyperbolicity is that so a variety is Brody hyperbolic if any holomorphic map from the complex plane into X is constant. So there are these 2 conjectures. So there's the Kobayashi conjecture, saying that a generic hypersurface in Pn plus 1 of degree dn is hyperbolic in this sense if the degree is sufficiently large, and the optimal the expected degrees are essentially linear, just essentially 2n, at least for a large n, and so then this has been proved for sufficiently high degree, originally Sue, Brotbeck, and then effective degree bounds coming down to but very large, n log n to the n, and then there's this other conjecture, the Green-Griffiths-Lang conjecture, which is saying that a projective variety of general type always contains a proper subvariety, such that every non-constant entire holomorphic curve is contained in this this subvariety. And again, you can think about projective hypersurfaces, and a generic projective hypersurface is of general type if its degree is bigger than n plus 3. So this has also been proved, well, in special cases, but also in general, but with very large bounds. And recently, there's been a very beautiful result by Riedel and Yang relating the 2 conjectures. So if you can prove the Green-Griffiths-Lang for bounds dn, then Kobayashi will be true for hypersurfaces with degree at least d2n minus 1. And so there's this basic strategy due to de Mailly for proving these conjectures in terms of these jet bundles. And so there's this reparameterization group, diff K, of the K-jets, holomorphic K-jets of maps from C to your variety X. And it's not, and it acts on this this jet bundle, and the action is, it's not a reductive group, but it is of this nice form. It's in fact of the form U hat. It is exactly unipotent semi-direct product grading C star. And so we were able to basically just tweak de Mailly's strategy that's been used before, and Greg is the expert on this, to enable us to get bounds for Green-Griffith slang, which are polynomial, at least, so polynomial of degree 6. So still not linear as would be hoped, but quite a bit better than before. And because of the Riedel and Yang proof result, then that also gives some polynomial bounds for Kobayashi as well. So yes, it's this this reparameterization group diff K, which is a semi-direct product of a unipotent group and the C star, which in many ways was the original motivation for looking at these U hats.
Thank you.
Yeah, I have maybe somewhat vague question. Do you think there might be some real C-infinity analogues of these of the story? I mean, where instead of a C star action, you would look at an R star action, and graded groups acting on graded manifolds? Yes.
Yeah. Certainly the it's really the R star that's crucial, because the circle you can so I haven't really thought about it in any detail at all, but I would I don't know. I mean, to some extent, the Kähler, the fact that you're playing off the complex point of view and the symplectic point of view is quite crucial. So I'm not sure that I mean, I think the group I'm not sure whether you could get rid of the Kähler structure, but you might be able to work with groups that were not necessarily complex.
Okay, any other questions? I don't see any raised hands. I see nothing in the chat. So if there are no further questions, let's thank Francis again for a very nice talk. I believe we have another seminar next week, Anton? Yeah,
there is a seminar next week. So thank you again, Francis. Thank you, everybody.
Okay, many thanks.
Thanks very much.
Bye.
Thank you. Bye-bye.
Bye.